Have you ever been completely overwhelmed by like a really complex topic? Like you just wish there was some kind of magic button to instantly understand it?
Yeah, I think we've all been there.
Well, today we're diving deep into something in AI that feels like it's getting us closer to that magic button. We're talking about ladder. It's this groundbreaking new method that seems to be a really smart way for AI to learn and solve super tough problems.
Right. And what's really cool is that it's not about just throwing more data or bigger models at the problem, which seems to be the trend these days.
Yeah, I was just reading about that someone trained a 10 trillion parameter model or something. Insane.
Exactly. But ladder, it stands for learning through autonomous difficulty-driven example recursion, is like a totally different approach to AI learning. It's about changing how AI, specifically large language models or LLMs, actually, understand things.
So we've been digging into the ladder research paper from Tufa Labs. And let me tell you, this is some serious stuff. It's super detailed and really well written. They even included a bunch of supporting notes to kind of help clarify things.
Yeah, the notes are great. They help me wrap my head around some of the more complex parts.
And for our listeners, what we're going to try to do today is unpack how ladder works at its core, why it's such a big deal in AI, and what it might mean for the future. How powerful AI could get, and maybe even how we think about learning.
All really interesting stuff.
Absolutely. And to make sure we don't get lost in the needs, we've got our expert here to help guide us.
Happy to be here.
Awesome. So let's just jump right in. What's the core idea behind Ladder? What makes it so innovative?
Okay, so at its heart, Ladder is all about getting LLMs to learn by like breaking down really hard problems into smaller, easier pieces. It's not about someone giving them easier questions. The AI actually figures out how to create those simpler questions itself.
Whoa. So the AI is basically dating its own study guide?
Yeah, kind of. And it does this recursively, like it keeps breaking the problem down into smaller and smaller pieces until it can solve them. Then it kind of works its way back up using what it learned from the simpler pieces to solve the original harder problem.
Okay, that's pretty amazing. They call this a natural difficulty gradient, right? Like a staircase leading up to the solution.
Exactly. And this is a huge shift from how we've been training AI in the past.
And what's even cooler is that Ladder doesn't need these massive data sets that have been carefully labeled by humans or even constant feedback from people to learn. How does it do that? Like, how does it know if it's on the right track?
That's where the real magic happens. Instead of needing humans to tell it what's right or wrong, it uses what it already knows, like from its initial training, to try to simplify a problem. But the key is that it needs a way to check if its solution is actually correct, and that's where this reliable verification mechanism comes in.
So it's like it's double checking its own work.
Yeah, exactly. In the Tufa Labs paper, they focused on math problems, specifically integrals. So the verification mechanism was basically a way to numerically solve the integral and see if the model's answer matched.
Okay, so let me see if I'm getting this. The AI sees a super hard integral. It thinks, okay, this is way too difficult, and then tries to make it easier while keeping the core idea of the problem the same, right?
Yeah, you got it. And then it uses this verification mechanism, which is kind of like a built-in calculator to see if its solution to the simpler problem is actually correct.
So it's like a continuous loop of trying to simplify, solve, and then check. And each time it goes through this loop, it learns a little bit more, right?
Exactly. The success or failure at each step informs how the model tackles the next problem. So it's constantly refining its understanding of the underlying concepts.
Okay, that's pretty cool. But how does it actually come up with these simpler versions of the problem? It can't just like randomly change things, can it?
You're right, it's not random at all. It's a really clever multi-stage process. So first, the researchers created this huge library of mathematical transformations. These are like operations you can apply to an integral to change it.
So like some of these transformations would make the problem easier and some would make it harder.
Yep. And they were really careful about categorizing these transformations based on how they would likely affect the difficulty of the problem.
Okay, so they've got this toolbox of transformations, and then what?
For every hard integral the model sees, it picks some of these transformations to try and create simpler versions. But if they found that just randomly picking transformations wasn't enough, they needed to make sure the simpler problems were diverse enough.
So what did they do?
They tried a bunch of things. One was generating these simpler versions in bigger batches, like 10 at a time, because smaller batches were giving them a lot of similar repetitive problems. They also did this thing called temperature cycling, which is kind of like changing the creativity dial of the model.
Temperature, you mean like the temperature of the model, is that a thing?
Well, not literally. It's this parameter that controls how random the model's output is. A higher temperature means more randomness, which can lead to more, out there ideas, while a lower temperature makes things more predictable. They cycled this temperature between zero point 0.8 and 1.4 to try and find a good balance.
Ah, I see. So they're like, okay, let's get a little wild here, but not too wild.
Exactly. And they did this other really cool thing. They started using persona-based prompting.
Persona-based prompting. What's that?
It's basically telling the model to think like a famous mathematician when it's trying to make the problem simpler. Like, they might tell it to think like Euler and focus on series, or think like Gauss and look for elegant patterns.
So they're basically trying to get the AI to approach the problem from different angles, like a real mathematician would.
Exactly, and this gives them a much wider range of simpler problems than if they were just relying on algorithms.
Okay, so this whole process of generating simpler problems, it's recursive, right? Meaning it can happen over and over again.
Yeah. So the first set of simpler problems can be used to create even simpler ones and so on. It creates this like tree of problems where each branch gets easier and easier.
And they showed example in the paper, right? Starting with this pretty nasty integral AO plus 1 dx and finally AO plus 1 dx, and breaking it down into simpler ones like OX plus 1 dx, then O1 dx plus 1 dx, and finally O1 dx ticks.
Yep. That's a great example of how the complexity gets reduced step by step.
But with all this automatic generation, did they run into any issues? Like, what if the AI accidentally makes the problem harder or even impossible to solve?
That's a great point. And yeah, it did happen sometimes. They found that about 8% of the problems they generated were actually harder than the original or just plain unsolvable.
Oh, wow. So what do they do about that?
Well, those harder problems didn't really help with the learning process because they couldn't pass the verification checks, but they did take up computing power, so it's something they're still working on improving.
Makes sense. So they generate these simpler problems, try to solve them, and then check their work with this verification mechanism. Can you tell us a little bit more about how that verification works, especially for the integrals?
Sure, so for each potential solution the model came up with, they had this really robust numerical verification framework. It basically involved picking random points within a certain range, in this case between -10 and 10, and then checking if the model solution and the actual integral were equal at those points.
So instead of trying to manipulate the integral symbolically, they're basically plugging in numbers and seeing if everything matches up.
Yep, it's much easier to do numerically, especially when you're dealing with complex integrals that might not have nice, clean, symbolic solutions.
Makes sense. Did they have any safeguards to make sure this numerical verification was accurate?
Oh yeah, definitely. They were super careful about that. For example, if one of the random points they picked happened to be near a singularity, which is like a point where the function blows up, they'd just pick a different point. And they also set a very strict threshold for how close the values had to be considered a match.
So it's like they had multiple layers of checks and balances to make sure the verification was solid.
Exactly. And they also put a time limit on each verification attempt so that the model wouldn't get stuck trying to solve an impossible problem forever.
Clever. And the paper specifically mentions why they chose this numerical approach over using symbolic methods. Can you tell us a little bit more about that?
Sure. The main reason was that numerical verification is much more broadly applicable. Symbolic methods are great when you have a good symbolic solver available, but that's not always the case, especially when you move beyond math problems.
So they were thinking about how this could be applied to other areas where a symbolic solution might not even be possible.
Exactly. Numerical verification can be used in a lot more situations.
That makes a lot of sense. Okay, so the model is generating, solving, and verifying, but how does it actually learn from this whole process? You mentioned reinforcement learning earlier.
Right, so the learning part is handled by this algorithm called Group Relative Policy Optimization, or GRPO for short. They chose GRPO because it's pretty efficient and it doesn't need a separate model to like judge the performance. Instead, it just compares the different outputs within each batch and learns from those relative differences.
Okay, so it's learning by comparing its own attempts, basically.
Exactly. Like if it generates 10 different simpler problems and solves 5 of them correctly, it can learn from which approaches worked better than others.
That's really cool. And what's the reward in this reinforcement learning setup? Like, what's motivating the AI to improve?
Well, the reward is pretty simple. First, there's an accuracy reward. If the model's solution passes the verification checks, it gets a reward. Second, there's a format reward, which basically encourages the model to present its answers in a specific way using these answer tags.
Okay, so it's getting rewarded for being accurate and for presenting its work neatly.
Exactly. And this simple reward structure was intentional. They wanted something that could be easily adapted to other domains beyond just math problems.
Smart. So, with all these pieces in place, what kind of results did they actually see? Did ladder really work?
Oh, yeah, the results were really impressive. In their first experiments, they used a relatively small LLM. It was a Llama model with just 3 billion parameters. They tested it on a set of undergraduate level integral problems.
Okay, and how did it do?
Well, before training with ladder, it could only solve about 1% of the problems. But after training with ladder, its accuracy jumped up to 82%.
Whoa. That's a huge improvement. And they also tried training the same model without the variant generation, right? Like just throwing the hard problems at it and seeing what happened.
Yeah, they did, and that totally failed. It didn't improve at all.
That really shows how important the difficulty gradient is, right? Like the AI needs those stepping stones to learn effectively.
Exactly. You can't just expect it to jump straight to the hardest stuff.
Makes sense. So they had success on these undergrad level problems, but what about something even harder?
They took it up a notch and tested the ladder trained model on the qualifying exam for the 2025 MIT Integration B.
Oh, wow, the integration bee. I've heard of that. Isn't that like super difficult even for really good mathematicians?
Yeah, it's notoriously hard, but the ladder trained model this time, they used a 7 billion parameter Llama model, actually did really well.
How well are we talking?
It got 73% of the problems, right?
73%. That's incredible. And that's better than some humans, right?
Yeah, much better than the average person. In fact, that score would have been enough to qualify for the actual competition. And get this, they also tested GPT-4o, which is a much larger model, on the same exam, and it only got 42% correct.
Wow. So a smaller model trained with ladder outperformed a much larger model that wasn't trained with ladder.
Exactly. It really highlights the power of this approach. And, this is not just about winning a math competition. It really shows how AI can achieve expert level performance on really difficult tasks through intelligent learning.
That's pretty mind-blowing. Okay, so ladder is clearly a big deal, but they didn't stop there, did they? They also developed this extension called test time reinforcement learning, or TTRL.
Right. TTRL is like taking the core idea of ladder and applying it during the testing phase. So let's say the ladder train model is working on the integration B problems and it comes across as super hard one.
Okay, yeah.
Instead of just trying to solve it right away, TTRL kicks in and creates a bunch of simpler problems that are specifically related to that hard one. It's like doing some targeted practice right before the big game.
Uh-huh. So it's like a micro-learning process, as they call it in the paper. The model realizes, okay, this is a tough one. Let me practice on some similar but easier ones first.
Exactly. And it keeps using that same verification mechanism to make sure it's learning correctly so it can actually improve its strategy in real time, even during the test.
That's so clever. And did TTRL actually lead to even better results?
Oh, yeah. When they added TTRL to the ladder training model, its accuracy on the integration B exam jumped to 90%. That's even better than OpenAI's O1 model, which got 80%.
90%, that's insane. And they tried using TTRL without first training with ladder, right?
Yep, and it didn't work at all. It seems like that initial training with ladder is super important for giving the model the foundation it needs to then benefit from TTRL.
Like ladder builds the overall strength, and then TTRL lets it specialize and become even better at specific tasks.
A perfect analogy.
So the big takeaway here is that ladder and TTRL aren't just about making AI models bigger or giving them more data. It's about making them learn smarter.
Right, it's a completely new way of thinking about how to improve AI capabilities, and the results are really exciting.
Absolutely. And they even mentioned that TTRL could potentially be parallelized, right?
Yeah, they're thinking about ways to make the variant generation and learning process happen simultaneously across multiple processors or even different machines that could make it even faster and more efficient.
That would be huge. Okay, so we've seen how successful ladder and TTRL can be for solving math problems, but what about other areas? Could this be applied to like totally different types of problems?
That's a great question, and the answer seems to be yes. The researchers think that this approach could be used for any verifiable domain. Basically, that means a domain where it's easier to check if a solution is correct than it is to actually find the solution in the first place.
Okay, so like what kind of domains are we talking about?
They gave a few examples in the paper. One was competitive programming, where you could have AI generate code and then automatically test it against a bunch of pre-written tests to see if it works. Another one was formal mathematics, where you can use these sophisticated tools to verify the correctness of mathematical proofs.
So anything where you can create different versions of a problem and then easily check if the solution is right.
Exactly. And they even talked about how this could be applied to things like planning and tasks that involve AI agents. Like an AI agent could learn by completing simpler subtasks before tackling the bigger goal.
And there would be a way to automatically check if each subtask was completed successfully so the AI would know if it was on the right track.
Exactly. The key is having a reliable verification mechanism in place.
That makes sense. So what are some of the challenges and like open questions that the researchers are still thinking about?
Well, one of the big ones is how to make the variant generation process even better. They talked about developing adaptive difficulty calibration. That's where the system would automatically adjust the difficulty of the simpler problems based on how well the model is doing. They also mentioned dynamic curriculum sequencing, which is figuring out the best order to present the problems to maximize learning.
That sounds really complex.
It is. And of course, there's always the challenge of balancing exploration, which means trying out new and different types of variants with exploitation, which means focusing on the types of variants that have already proven to be effective.
And even with ladder and TTRL, they still couldn't solve every single problem from the integration B, right?
Right. There were two really, really hard ones that stumped even the ladder and TTRL enhanced models. So there's definitely still work to be done.
For sure. But it's amazing how far they've come. So to wrap things up, ladder and TTRL are a pretty big deal. They're not just a small step forward. They're a whole new way of thinking about how AI can learn and solve problems.
I totally agree. It's not just about brute force anymore. It's about strategy and intelligence.
And it might even have implications for how we learn as humans. Maybe we can learn something from how ladder approaches problem solving.
Yeah, definitely. I think the ideas of breaking down complex tasks into simpler steps and constantly checking your understanding are really valuable no matter what you're trying to learn.
Absolutely. Well, thanks for joining us on this deep dive into ladder and TTRL. If you want to learn more, we highly recommend checking out the full research paper from Tufa Labs. It's definitely a challenging read, but it's worth it.
Agreed. It's a fascinating paper.
And as always, let us know what you think. We love hearing from our listeners.
Yeah, let's keep this conversation going.
Until next time, keep exploring.